You do have start. And this is really a pleasure to have Pablos here, because as many of you who have been here at the CFA for a while know, he originally, when he came to Harvard, he started here. And a lot of us had the pleasure of interacting with him and really experiencing his great enthusiasm and the fun that he has working and that we have when we're working with him. So I'll just give you a few quick facts, which you can also find online, which is that he did his PhD at the University of Pennsylvania. I knew that. And that even there, he was really one of the pioneers in terms of networking and large computer projects and grids. He had experience in medical imaging before he even came here. So he did a PhD, which was very physics related. He has been doing astrophysics in a number of different contexts. He is an expert on time series. And a lot of us rely on him when we have a question. We call Pablos and say, okay, you know, how do you do this? What should we do? And so it's really a pleasure to have him as part of this seminar series. And I'm sure all of you are looking forward to what he has to tell us today. Thank you for being here.
Thank you. It's dark. Thank you, Roseanne, and pleasure to be back. I haven't been on the observatory for about a year, and I almost got lost again coming here. So I've been here for, 8 years before I now most of the time down at the main campus at the Institute for Applied Computational Science, which is part of the engineering school. So the original title is Building Training Sets for Astronomical Data, but the paper associated with that is Probabilistic Survey Design, Crowdsourcing with Evolving Annotators. I'll explain everything. Roseanne told me to make it simple. I'm not sure about that. I'll try my best. So this project started when about 8 years ago or 10 years ago, we started doing using machine learning to automatically classify objects in the sky, celestial objects. And some papers came out, not just us, other people, and we all started doing well. And we thought, okay, this is good progress, this is the way to go. But at one point, I think I was at the talk, during the talk, I just realized that a lot of things depend on the training set we have, meaning depends on where we have ground truth. And then I start looking around and I realize our training sets pretty much suck. They're incomplete, they're put together in a haphazard way. If you ask many astronomers, they don't agree on the classification we have. So I felt, okay, so if we're gonna do something serious and will lead to some discoveries, we need to solve the problem of the training set. And that's where the story started. How do we build training sets? And so here is the outline of the talk. First, I'm motivated. I will talk a little bit about previous work, our model, the results, and some things we're doing now, which are, for me, very exciting. Okay, so motivation. So first of all, let me define what is a training set. The main bulk of machine learning, or nowadays, the keyword is AI, is supervised machine learning, which simply means either regression or classification, but you give the machine or the model some examples, and the model learns from the examples. And once you learn from the examples, you can apply it to something else. So that's called supervised learning. And the training data is where the examples are. So this is the formal definition, but again, since Roseanne told me to keep it simple, I'll do a cartoon demonstration of that. So we start with some labeled data. Labeled data are data that we do know the ground truth. We do know if it's a star or a galaxy. We do know if it's an eclipsing binary or a supernovae. So you get people, and they label the data. Once you have labeled data, what you usually do, you split them into the training set and the testing. The training set, you use it to learn the model, and the test, you use it to test the model because you never seen this data. And you make an evaluation. And once you have tested the model and you learn the model, you apply it on everything else. That's as simple as that. So blah, blah, blah. Okay, so now, so what does a training set look like? I keep it simple, Roseanne. Okay, so we have cats and dogs. So you go there as an annotator, which now it answers your question, and you put labels. This is a cat, this is a dog, dog and cat. Once I have that, I'm going to use that to train my model. So what is the problem with the training sets? Well, don't believe what people say. Size does matter here. So the bigger the training set, the better the results are. So let me explain that. The x-axis is the training number of training examples, and the y-axis is how well we do. So if you look at the green line, is how well you do on the test set, and that's what you care. So you want to do well at the training set. In the training score, actually, the score goes down, and does anybody know why? The reason is, down here, if you don't have enough examples, you overfit. Your model learns the particulars of the training set. Bigger your training set, less you can overfit. Okay, so it's called regularization. So that's why this is going down. But the main point is that the score I care is the green line, and it gets better with the size of the training set. So the more training sets I have, the better I'll do. Okay, it's not so simple because quality matters too. So in this example, another simple example, I show to the model a lion, a tiger, and an elephant. It learns this, but then I show to the model this animal here, and the model will have to say something. Most likely it's going to choose the elephant because you have a long task, right? Because the model never seen this animal, it would never know what to do with it. So also, you look at the pictures I have here. The lion is sitting nicely there, posing. So is the tiger and the elephant. But in reality, what you want to have in your training set, you want to have diversity. You need to have as many different examples of the same thing. Okay.
Carlos, if you did show the machine something that would just naturally happen in your full data set that hadn't been in the training set, isn't there an option that says none of the above, this isn't something I can classify, or is it a low probability of classification?
Yes.
Some way that you would tag it, you would see it and say,
yes.
There's something strange in this one.
You can abstain. You can say if the probabilities are not high, I'm not going to do anything. However, the classic thing, you get the probability of this, a probability of this, a probability of that, and you take the maximum. So that's the vanilla classification thing. So in this case, most likely this will be the higher probability, and it's just going to pop up an elephant, which is not an elephant, of course. So far we know training needs the size, and we need diversity and the quality. Now, to make the case even more, I think in the news almost every day now you hear something about AI has done that, and we can do speech recognition, language translation. These things have been out there, and they're very successful, no doubt about that. But let me make another point here, is that if you look at in the history since 1985 and now, so let's look at that. So, for example, statistical machine translation algorithm, translate from one language to the other. The first paper appeared like late 80s. However, the success started in 2005 when Google harvested websites that they were translated for 2 different languages. They used that as a training set to train the models. So it took about 20 years for the algorithm which was there to mature to be successful. And the reason is the training set. The same happened, this is the Chinese translation, the same thing. The same happened with the convolutional neural network algorithm, appear again late 80s, early 90s. Now convolutional neural networks are everywhere. But why? Because in 2009, ImageNet came, and ImageNet is, at the time I wrote this paper, was 1.5 million labeled data. There are a little more now. So basically, people sat down, take images from the web, and label them, hand-label them. And they label a lot of them. So once that data set became available, boom. the Google object classification near human performance appeared a few years later. So this pattern appears in many other things. Even for chess, when the Go player, is the training set that enable all these algorithms to be successful. Okay. So what is the problem? Why don't we create more training sets? We can put, a lot of us start labeling things and create training sets. Well, can be extremely hard. It's not obvious sometimes when you show you a galaxy or a star or something varying this way or it varies a little bit different to identify. It's not easy. So it's very expensive in that way. There's too many labels for each object. Sometimes they're not orthogonal. And it's not easy to accurately discern among all possible labels. So labeling, it's a hard problem. So right now I'm going to explain all the possible ways we have in order to create training sets. It's not just for what I'm going to talk today, but just a review of the different ways of creating training sets. Okay. So let's do. So the first one, I call it manual or visual inspection. You have a bunch of unlabeled data, and there's docs, and we go and we label them. That's the classical way. Another way is called active learning. So active learning, you label some data, and then the model decides which of the unlabeled data you want to label next. And it's kind of simple concept. If I have elephants and tigers, I have enough examples to distinguish them, but the difficulty becomes on animals between, emu and an ostrich. That the model will have difficulty there, so you want more labeled there. So this is called active learning, and the idea is that you're trying to manually label, things that the model is having difficulty with. Okay. Another way of doing it is called synthetic data augmentation. So if, and actually this is something we'll start doing now, if I know how to build a star from simulations, I build stars from simulations, and then I create time series from the light curves from there. Or I can create, from Cosmos simulation, I can create galaxies or whatever. So this is using actual physics to create synthetic objects, and then we have them as training sets, because we know what we create. Of course, there's a problem with that, because there's a limited phase space that you can explore. You don't know where the limitations there. And your model may not be complete. And finally, that's another interesting topic, but not for this talk. Is called transfer learning. Transfer learning is when you have a training set in one domain and you want to transfer it into another one. For example, if I learn how to understand a language in English, can I use the same model in Italian? So actually that's not a very difficult task to translate something you learn from one language to another language, because especially English and Italian are very similar, or Spanish and Italian, that would be similar. However, going from English to Chinese, that's a much harder task. But the idea here is that if I have a training set, for example, from candles, I can transfer it to something else. Right? So the transformation there has to take care of some of what's happening between one survey and the other survey. Okay. So this is what I call everything you could do. So back to my, let's look at manual visual inspection, which is what I'm going to be talking today. So let's look at it in this way, crowdsourcing. Crowdsourcing is when instead of having one person doing it, you get multiple people to do it. So if your annotator or the person who puts label is going to make some mistakes, he gets for some reason tired, or had a drink before we start doing it, you want to be able to use the power of the population to get better results. So let's look at this. So we have the cats and the dogs, as usual, and then we ask someone to label this animal here. Okay, so obviously it's a dog, but now let's look at it in a different way. In this scenario, I have the 3 dogs, 1 cat, a fish, and a mouse. And then I ask And it is, everybody together decides if it's a dog or not, okay? So these are my votes. So sorry, I didn't say that correctly. So I start with that. I ask this, and then these people vote accordingly. These 3 people vote for dogs, this for fish, this for cat, and this is for mouse. Okay? So this annotator, for example, is very confused. All right, so this is the dog. Okay, so let's look at this example. I have a nice little lion here, puppy, and I ask these students to give me votes. And if you count here, there are more cats than lions. And so the decision is that it's a cat. Okay? So this is majority vote. And we kind of know by now that majority doesn't work very well. So actually, majority does work. It's the electoral thing that doesn't work. But we've seen examples that majority may not be the best solution to these things. So if I knew that some of these kids are not paying attention, and you can see most of the boys are not in good shape because they're not paying attention, I'm going to weight differently, or I'm going to exclude them. And now if I count, I have 7 lions and 2 cats, so that's line. Okay, so that's the basic idea of using the crowd. And the basic idea of using the crowd is, one is to use majority. The other one, now I'm weighting different annotators differently. Okay. Any questions so far? Pretty straightforward. All right. Now, challenge number 2. What kind of questions do we ask? So if you go, this idea actually came to me when I went to check my eyes. And then the doctor does not give you, here is 10 things, decide which one is the best, right? He says, better, worse, better, worse. So I think it's well known that we're much better at choosing something is better or worse, or A and B, than having to choose among 10 things, right? So if you have a choice to do something and you have 20 choices, you get overwhelmed. But if you just say, should I go left or should I go right? That's a much easier decision to make. So here is, again, we explore this idea. I have my dog here, and I can ask, is it a dog, cat, or a rat? Okay, that's kind of straightforward. You're going to choose the dog. But then I have this animal here, and I ask, is it a bull, a hay mule, or a reindeer? What is it? Much harder problem to answer, right? Unless I change it to the following. Okay, it's obviously not a bull. We all know that. But, so I can ask, yes, I can ask the full, what we call ABCD query. So you have to choose that this is a hay mule, which is actually a hay mule. Or I can ask first, is this an animal a bull, yes or a no? And we call this a yes and no query. So that makes it easier in principle, and we're going to show that. So if you do the yes or no queries, what we claim is that is less effort, and then you get partial information from this yes and no, which this partial information together can gain of. Okay? So let's recap. So I talk about why we need training sets. I told you the 4 different ways that I claim to create training sets, and now I'm focusing on the crowdsourcing. And now I'm going to be talking about how do we do it. Okay. So, okay, I'm good with time. So the first paper I found to do this is by David Etzkin in 1979. They use actual probabilistic way of doing it, and we're trying to copy that at the beginning and then expand from that. And the way it works is that you recover the true labels, you weight the votes, and then you do a probabilistic model. Let me actually be more specific. Actually, no, this is it. So we're going to use something called EM algorithm, which I'm going to explain in a second. And the advantage of this thing, in essence, what you're trying to do is trying to figure out what's the true label, but at the same time, trying to figure out who are your good annotators. So the problem is a little bit harder. Because what I said before, if I knew who is good, I'm going to weight their votes higher, and who is not a good annotator, I'm going to vote their votes less. If I knew who is good and who is not, that's a different story. I go and take the votes, I weight them, and then sum them up. That's an easy problem. The problem here is that I don't know who is good and who is not good. So I'm going to try to do these things together. figure out who is credible and who is not, and at the same time trying to infer the true labels, the true type of dynamic. Okay, so I'm going to give you a little preview ahead. This is kind of the literature that we explore. So the Minsky model comes this way, and this is the first part of the talk. And then here I stop and go back, and the title suggested that we're going to explore annotators with different credibility, but they change in time. Okay. So let's start with the proposed model. And this is where it's not simple anymore. So let's first look at the full question, what I call A, B, C, D. So I have a probability to say it's a dog, and in reality it is a dog. And on this particular person is 100%. If I show that person a dog, the probability of say cat is 0%, so it's very good at finding dogs. However, if it's a cat and I ask if it's a cat, there's probability 33% to say it's a dog and 67% to say it's a cat. So this particular annotator is very good. If you show a dog, boom, it gets it. If you show a cat, sometimes it gets confused. So we represent that as what we call a confusion matrix, and that represents the true label is in this axis and the predicted label is in this axis, and that represents these probabilities. Okay? So far, so good. Now, with the yes or no questions, things change slightly, but not much. So in this case, if I show any of the true class, and the true is yes, what's the probability of saying yes is 92%. If it's yes, I say no, that's 8%, and the other way around. In this particular case, I'm conditioning on what the thing is. So this we call a credibility matrix. So if we do it for the generic case, so the true class is M, K, and the query class is MK star. Let me explain this, a little bit confused. I have a dog, and I ask someone if this is a dog, or I have a dog, and I ask you, is this a cat? So there are two different questions, and that's represented by the K prime. So this is the true class, and this is. Because for each one of them, I'm going to be asking questions, not only the true one. If I have a dog, I may ask, is it a dog? I may ask, is it a cat? And if I have a cat, both ways. So by doing that now, I have the full, what we call credibility matrix, and this is the true class, and this is the question I'm asking. So for each true class, there are multiple questions, and so I get the full matrix. And since I have many of, okay. So this is going to come, sorry. So I have to stop here and explain where I'm going to go. I'm going to model everything probabilistically. And when you model things probabilistically, there's something called a generative model, and I think I need to spend a minute explain. So when you do generative models, sorry, it's not in the slide, so you have to listen to me for this. You're playing the following game. You say, if I know how the whole dynamics of the system, if I know the dynamics, if I know the probability distributions, I can generate votes. So for example, I'm going to play the game. I have three annotators, 1, 2, 3. I claim I know their credibility, and I claim I know the true labels, and I'm going to create, based on what I think is their credibility and what I think is the object, I'm going to create votes. Okay. So I create some votes for a particular set, and then I compare it to the true votes. If they match, good. That means I guess the credibility right, and I guess the correct label right. If they don't match, I start changing your credibilities or the true votes until I get the two match. So that's what generative model means. You generate data based on what you think the dynamics are, and then you compare it to the true data using the likelihood function. Okay, so let's do that. So I have this thing that represents the probability of saying yes or no in a particular question. So this is a random variable. It's any variable. I'm going to have to infer it at the end. So I need to give it some distribution, or a prior distribution in this case. And which distribution gives me from 0 to 1 is the beta distribution. That's where it comes from. I don't know why it's beta, but it's the only one I know how to give me from 0 to 1, and it represents, it's very standard thing. Okay, so that's That's represented here, and k goes from 1 to k. This is the questions I'm going to ask. And there is this theta is what I described before. So every one of these little elements here are drawn from this distribution. So this is for one annotator, and for all of them, I have one of those two. All right, so I almost created a monster now. I have multiple matrices, and I'm going to be guessing all these little things here, and I'm going to be guessing the true label, and I'm going to be comparing to the votes. So where am I? Here. Okay. Now I also have the true label, which I don't know, and I call it Z, and I claim it's come from categorical, and you may wonder where is it coming with these things. It's the only choice I have, because this Z can be any of the classes: star, galaxy, black hole, whatever, or cat, dog, mouse, whatever. So the only thing I know is going to be one of those. So it's like throwing a dice down, and that's what categorical does. And this little p tells me what is the proportion of each one of them. So it's the natural thing to do. All right, so now I'm putting it all together. So I have the theta that I described. I know how the Z is modeled, and now I have this R. Let's connect them, and it's connected. The votes you're going to give me depends on your credibility, and it depends what you see. What you see is Z, and what are you is theta, so together they give me that. Okay? And one more detail is we put this gray because that's measure. That's not a random variable. This is a random variable, I don't know it. This I don't know it. This I know it. So if you put it all together, you find the probability of R given the theta and the Z. So it's the probability of giving me these votes given I have such an annotator, such a credibilities, and the true one. All right. All right, so now I'm writing the whole probability down, and because they're all independent, I multiply them. This is just nothing more than a Bernoulli. You just either you vote yes or you vote no, and depends on your theta, and it depends on the actual vote you gave. Okay? So once I have everything together, in principle, I can just solve this thing. And how do we solve this thing? Generating model. I'm going to create a simulator, an MCMC, who is going to generate these things, and it's going to be comparing to the votes, and I'm going to be walking around, changing my thetas, changing my Z until I find the best. Okay? That's the basic idea of a generator. So that's an expensive proposition, but it's a well-known thing how to do it. We use in MCMC, Monte Carlo Markov chain. Jesus Lord. So it's a way to sample. Okay. All right. There is one problem here. I think the problem I'm putting on is too difficult because I need to figure these things and these things at the same time. You can imagine a scenario that I can change my annotator strength, switch them, and change the labels such as give me exactly the same votes. Okay? So this is called identifiability problem, meaning that I cannot narrow it down to one particular set of annotators' credibility and one set of things. So this is a known problem. We face it when we first submitted the paper. The referee came back and said, hey, this is a problem. You should do something about that. So we went back to the drawing board and we learned how to deal with that. And this is what's called semi-supervised way, and I'll explain. So on the right is what we have before. On the left, I do something else. I'm going to give my annotators few examples that I know the answer. So now Z becomes gray, because with that Z, I know the answer, so at least now I only have to deal with that, so that switching cannot happen anymore. And what we found out is that you don't need many of those. You only need very few examples, and I have plots to prove that. You need very few examples in order to break that symmetry that we have before. Okay, so what we did, we give the annotator some examples, we know the answer, we solve the same problem, now it's easier. And once we solve this problem, I use this as a prior to this, and this, the row that determines Z as a prior to this, blah, blah, blah. So this is a little bit technical details, which you don't need to know. But the basic idea is that if I give some examples, I know the true answer of the labels of the type of animal I have, I use that to break that symmetry. Okay. That's irrelevant. The rest is we go and run it until. With one exception, I want to talk about how we do it because I have this dual problem. I need to know the credibility and I also need to know the true label. This is where the EM algorithm comes in. So it's very kind of intuitive. So it's called the E step. I'm going to compute the probability for each possible value of z given theta. So I assume I know theta. I know the credibilities. And given that, I find z. Once I find z, I compute theta from that z. And I keep going. So that's kind of iterative way. It's a way to solve this problem. Standard methods, been there for a while, and we use it for that. Okay. So this is just how you go from likelihood to posteriors and all these things. I can skip those, right? So once I have the probability distribution, I just sample until I get my best result. Okay. So we use nuts to do that because this sampling problem can be very, very tricky and it takes forever. This is a version of MCMC that is faster. And we use something called variation inference. How many of you have heard variation inference here except from Mike and Rafa? It's an approximate way of doing it. It gets faster, but you really have to work hard to get the mathematics right. There's something called black box variation inference, which hides the mathematics. Anyways, we use that to speed up the process. All right, so now let's go to the results for this example. So we create three scenarios. One, you always start with synthetic. So we have a control, we know what we're doing, so we can at least make sure what we're doing is work. The second one is we use, instead of annotators, we use models. And the third one, we did an actual experiment with people. And trust me, humans, not easy to deal with. But, okay. So the synthetic annotators and data, so what we created here, we created synthetic credibility matrices. So we create annotators with some credibility. We create synthetic votes based on that. So for, we create different proportions of our sample, of our classes, and we create unbalanced and unbalanced things. So we try 1 zillion kind of simulations, changing the credibilities, changing the number of classes, changing the number of annotators, all kind of experiments to make sure that our model works. Here, what I'm showing is that when you do these MCMC things, there's one problem you always have, is you don't know if you run it long enough. So this is basically checking if I converge, and these plots say they do. And this is the results we got for a particular one of the experiments. Is basically the green line. This is the number of options within the training set. This is the yes and no query. You can see it's doing almost perfect here. The majority is slightly below. But what I wanted to show is that if you see these lines here, it's individual annotators. None of them is even close to that. It's only when you combine it. And this thing one is kind of the majority vote. So you can see the majority vote is not doing well. When you use A, B, C, D, so you ask people to vote any of the four, it's slightly better. And we use a yes and no query, it's even better. So that's kind of good news. It means that at least in synthetic scenarios, our model works very nicely. The next one was the classifier as an annotator. Now, instead of creating people, we use models to be the people. So it gives us a little bit better results, and we get real data now, not synthetic data. So what we did is we got data from, this is Ogle data, or Catalina, Ogle data. So these are the different classes. We have eclipsing banner, B stars, long period variables, Cepheids, so 4 classes. So we have real data, and now instead of annotators, human, we create models. Again, you see that one thing we examine is that, you remember, I have to make some assumptions about my priors. We see if sensitive to these priors. We're not sensitive to the priors, which is good. And what you see here is the error I get, because we know the true labels in this case, and then we can go back and test. As you go this way, you can see that the error is decreasing, and with only 1528 objects is enough. You remember I have this semi-supervised. If you give 15 to 20 already, the error is become very, very small. Okay, so that's about that. So now I'm going to go into the real problem, the real thing. So we create two scenarios, one from Catalina survey, which has all these variable stars, and then we did another one we get some data set with animals just to test it. So the first one, we created a website, and we all went to vote, about 15 of us, and we just showed the light curve, some other information here, and then the only thing you have to vote is yes or no. Is that a Cepheid or not? Okay. So that was a good experiment, and we start voting, and then we're trying to use the model to decipher the true label. Though we have the true labels, at least what Matthew Graham tells us is true label because he did it. Though he was one of the annotators and he didn't do so well. I was the worst, surprising. So we used this data at the end. And we also did one, this is a student of mine from Chile. So she used her friends from Facebook and Instagram. And she's asking if this is a reptile or not. It's kind of obvious, and you'll see the results. So anyway, so they have to choose if something's a reptile or mammal or something like that. All right, so here are the results. So these are 6 annotators. This annotator gets 73% overall accuracy, and this one gets 63%. Guess who is that? That's me. But I'll show you in a second why. There's a reason for that. Now, none of them gets better than 73%. If we combine them, where is the overall? Here. Yeah. So this is, if we combine them, we go to 91.2%. And if we combine them with ABCD, we get 90%. Small difference, but it's there. So we have 16 annotators. We call ourselves experts in this case. And I don't mention here, but if you do majority vote, it's about 87%. Okay, so it's much better, 85%. So it's much better to do this. So the same happens with the animals. Unfortunately, the animals, everybody was getting it right, so it was a useless experiment because it was so obvious. You saw the penguin and asked if it's a reptile. My grandmother could do that. So, all right, so this is kind of what we see here. So I'm skipping couple of slides because I want to get to the other fun part things. Okay, so when we look at the data for the stars, I was surprised I was the worst. I think I'm the best. My mom thinks that too. However, if you look at the data, so this is a classic example. This is a very good annotator, gets them all right. This number 2, something happened here, and if you continue here, it's getting much better. So something happened here, and all of a sudden, he's getting it right. This one is random. So something happened there, and the annotator changed. So that's the question. Do annotators are always the same? All so far we've done, in all the literature we've seen so far, they assume the annotators, or the people they label, are all the same. But is that true? No. We see it here, and we have other examples. So we changed the problem. Instead of doing the above statement we talked before, we're changing the problem now. We're adding when annotators evolve over time. Okay? So there's 2 ways that people evolve over time. They age, and they get wiser. No. So one is you change independently of what you see. You just change, right? So either you get, as I said, wiser and older, or you get tired. So we came with 2 models. One we call fatigue. If you're sitting there and you're doing these annotations, after a while you start randomly hitting things. You get tired, you want to get over with it, right? Has anybody of you done any of these surveys? Galaxy Zoo or something? Yeah, after a while you start getting tired and you're just rushing it, right? So this is what we call fatigue. And the other one is what you saw before, which I call the epiphany. Something happens to the annotator, all of a sudden you're getting it, right? So you maybe see 3 cats and you think it's a dog, but then all of a sudden you look and you say, oh, whiskers, that's the key. I should call these cats, right? And this is what happened actually with the experiment we've done. Some of the people that were not experts, all of a sudden they start studying and they're looking. We have a leaderboard, which they had a 6-pack beer. So they got motivated and they start voting, looking at the how their things were changed, and they're learning, so they became much better at that, and they were getting it all right. Where I was playing the game fairly, I kept voting what I thought. So this is called epiphany. So we model that, happily, and that becomes a little more complicated, but we model it. This is the annotators we have. This is the true one, how they are. Actually, this is for simulation, sorry. This is the true. We create these annotators. We call them workers now. And because it's a different student who did this. So the red one is the true one. We simulate them. And then with the blue one, we're trying to infer it. So we're able to infer the changes on the annotators. Okay. And we did apply it on the real data. And now we have seen an improvement. The red one we call it static, but it is the evolving annotator. The name is misleading. This is the actual annotator who we model as evolving. Okay. All right, so that's so far so good. We have modeled the annotators changing with time. We modeled them statically. Now, am I done? Not yet. There's one more thing I want to talk about. I have 10 more minutes, right? Okay. So we're going to do an experiment. And you have to collaborate with me, otherwise the experiment will not work. Okay? So halfway is group A, and half that way is group B. Okay? So you're going to have to vote for me. Group B now have to close your eyes or look away. So I'm going to show you some stuff, and you raise your hand if something is, if you think is healthy or not. Okay? Ready? Okay. So is this healthy or not? Okay. This one? Yeah. How about this one? Okay. This one? The astronomers, they can. And this one? All right. Now, group B, open your eyes. Group A can keep your eyes open. So you have to raise your hand if you think something is healthy or not. Is this healthy? This one? This one? Excellent. This one? Okay. This one. Okay. Here's the thing. When I show you the granola, group A, only 2 people raise their hand. When I show the granola in this group, about 6 or 7 raise their hand. Because the reason is you saw a lot of unhealthy granola was, hey, that's a healthy one. The previous one, you see healthy one, granola is not healthy. Okay? So this is conditional. Okay? And I'll tell you. So we went ahead to model that. So I already knew the results, and thank you very much for feeding my experiment. Because I've done it before, and I always get about that right. Yes, it was quick. So, but if you think about this, we get condition, right? If you see something before, you get condition. Okay. All right, so this is the model, another monster. Now, what you see here is that the credibility changes from your previous credibility plus what you saw before. Okay. So this is a hidden Markov model style, same thing I was talking before, and we're going to model the whole thing again, and look at the results. Look at the improvements we get. Huge. Because the annotators, sometimes they go up, sometimes go up. It depends what you see before. Okay. So now I give you the bad news. The bad news is that it's very hard to find data that this helped. This is actually perfect. It was like given to us. But everything else we try, it's very hard to see the difference. And what actually means is that if you look at this one, once you have a lot of annotators, as you see, majority actually takes over. This was an amazing set. We actually removed some stuff out to make it happen. So it's not totally honest what I'm showing. We took the original data and said, what if we use this? How will that work? And so we have some intuition. There is one application that we found that people want to use it, and it's not in astronomy. Guess what it is? What do people get conditioned? Dating. It works remarkably well. If you see 3 very attractive persons, the 4th one is average, you say no. If you see 3 first not attractive at all, or you're not attracted, and the 4th one is so-and-so, you say yes. It's incredible. So there is a company in New York start using that to increase their dating thing, right? Now, I don't care about that. I'm married, everything is fine. So there is though another thing so I don't have much to say, just to conclude. There's another thing we're exploring now, is not to figure that is, can we turn the problem around? Can we change the sequence in such a way to condition people to give us the best results? And that's what we're working right now. So we know how to model it. It seems to be working. So now I'm going to be playing with the sequence in such a way so I get the best credibility, the best votes from everybody. All right? So, any questions? Yes?
What was your problem with the Safians?
What was the problem with the Safians?
With the Safians, yeah. You said that you got it bad, got it wrong.
I was getting it wrong because
Were you fatigued? Did you have an epiphany? What was it?
I never had epiphany. I was just bad all along. I was 67, 68%. I think the original, this is a long story. We have arguments that is going on. I think the original labels may not be right, but anyways, I believe Matthew more, I believe myself. Anyway. All right, so conclusions. I think the conclusions are, so yes and no query seems to be working. This paper is published. I think that I hope I convinced you the training sets are very important. We use this nuts implementation. You may not care, but it's a nice piece of code if anybody wants to use it. We create these 2 databases. Now people can play with it. We make it available. And we're working on the evolving annotators. Works on simulation, actually. Now it works on the real data, too. But, okay, I didn't change the slide. And so we're still working on that. And this is what I was talking. We're trying to optimize the sequence in order to get the best result. That's it. 50 minutes, right? Any questions?
Well, I have a question. One thing that a number of people in this room might do for astronomy is do exactly what Galaxy Zoo people do, right? And this is becoming, for your NSF proposals, for example, they love this type of thing. But when you do it, you'd like to do it correctly. So, for example, for identifying microlensing events of a certain type, for example.
By the way, we have a website you can plug in your stuff easily now.
Okay. So this is the type of thing that we might want to do, and say that we're including this as a kind of a way to do more of the work, and also to engage the public in the work.
Mhm.
Actually, have this be something that makes a difference in a larger sense. So I would imagine that there are variables that aren't even quite there. I know for myself with Galaxy Zoo, I might do 5 or 6 and get bored, and then just stop. And then maybe a month later, I'll come back and I'll be showing some students, and I'll do another few. So that's one sampling method. Someone who experiences fatigue might sit there and do 100 of them, and then they're really getting bored. So number one, how do you take that type of thing into account, or is that going too far? And second, can we just come to you and say, we would like to do something where we're classifying, I know you know microlensing already, maybe something else.
Yeah.
Can you help us make this into something that would actually
Sure.
fly, that we could really do and be realistic in our proposal?
Okay, so what was the first one, Roseanne? I forgot.
Well, if you have annotators who have really...
Okay, so the way I didn't explain this, but the way with this yes or no works, you don't have to answer all the questions. If you stop halfway, it's fine. We don't have to ask you for all the classes. It still works if you have multiple annotators. So if you stop and come back, and if you don't finish, still fine. The experiment I showed you, some people did not finish. They only did 100. Some people do 2,000. So it's okay. That problem is, no. Yes, it's robust. That doesn't matter. If you look at how we do it, it doesn't matter. The infrastructure, it's an important thing, how you put a website together, or how to set the experiment. And we have the code. It's easy to just give us the thing and we adapt it. Yeah, you can come to me for sure. There's one more thing, though. I don't know if I should get into that. Let me go back. It's not relevant to this, but you can see I start doing something and then I diverge to other problems. Where is my? So if you look at this page, right, this was done kind of haphazard way. We say, okay, let's put the light curves here, and let's put some of the stuff there, and then you do this, right? There's a whole field of people that they think how you can help someone to decipher between two different things, right? So there is a group at CIS that I work with them that maybe this is useless, you don't want to have it, maybe this is it. And the way we approach the problem, maybe I'm taking just one minute for that. The way we approach the problem is to measure how much you trust the model. So we measure trust, and we adjust the visual parameters until we increase the trust. And trust is what matters in this business. If you can trust, it means you can understand what is going on. Well, that's a different story. But yes, number 2 is that, yes, come and talk to me and we can Yes?
Can we not apply this up-down probabilistic model to peer review?
Say again?
Peer review.
I'm
Referring papers.
sorry.
Can we apply it to referring papers?
This up-down, your yes and no probabilistic
Can we try
model,
that?
It appears to me should work for peer review.
Oh, yeah, why not?
Well, figure out ground truth first.
Sorry?
Figure out ground truth.
You don't need a ground truth.
No.
If
This is a very interesting.
the ground truth is a latent variable, I infer it.
Yeah, but how do you train it without having at least some papers that you know are good?
It's called archives.
You can do few of them. And as I show, you only need very few of them. Yeah. Once you have about 10 of them, it's enough. It breaks the symmetry identifier. But do you know any editor who is going to be willing to do this?
It will make my job a whole lot easier, that's for sure.
But that will only serve to approve or reject, but the comments part, you cannot replace it with, this seems to be a binary thing,
Yeah.
yes or no.
Yeah, I think even a yes and no up and down Facebook type of thing, I think would be probably a more accurate indicator of the paper's worth than any.
But you wouldn't have the comments.
Well, you could develop this later on into another model, perhaps. Yes, with comments, you could sort of make that into a part of the quasi-refereeing process. But I would imagine that if there's enough statistics with just up, down, yes and no,
So that's
it
basically how editorial
would
reports
make better
work.
refereeing process. So
Many journals work that way.
No, but
The editorial report says up or down, and then they send it out to review if they say yes.
yeah, but the difference here, not every referee is equal here.
Right, yeah.
If you're a bad referee, your yes doesn't count. That's the whole point. Right? Yeah, I don't see why not. I mean, in principle, it should work.
I have a question. Not about paper, sorry. So it looks to me that the M algorithm helps you when you don't necessarily have a ground truth, because you can kind of wait.
If I have a ground truth, I don't have to do this.
Right.
That's
right.
the training set. I'm trying to discover the ground truth.
In most of the cases, when you're trying to deal with this kind of light curves, you might not have a ground truth, because you can have experts who think differently of a particular light curve. So do you actually need to have a ground truth at all when you do this kind of...
Okay, now I understand. Let me rephrase the question. First of all, let me make clear. The whole point is to discover the ground truth. Okay. This is when I put the ground truth, the little ground truth tree is for the thing to converge faster. Otherwise, it takes too long and you have this degeneracy, basically, right? Yet, we are able to find, even with no, it still works. Not as good, not as fast. It may take a day before I can give you an answer. But very few ground truth is all you need. But when I'm saying few, I'm talking about, this was a data set of 10,000 objects. We needed 10. 10 to 20 is enough. Because those break the symmetry. The only thing what you call a ground truth does is breaks the symmetry, and that's all you need.
And quickly, so this seems very good for when you actually have a test set in which all elements in the test set are represented in a training set. What happens when you have very rare objects that might not be appearing in your training set, and you test this on a test set that actually has very rare objects not present in the training set, so something that has not been labeled?
I think you're missing the point. The whole point is to put labels.
No, right.
Once I have the labels, that's a different story.
Right, but some objects that you think of LSSD.
Okay, so I have some objects I don't have labels. This exercise is to create labels. If you don't create those once you try your training set and you model it, those you're gonna fail.
Well, Raphael raises a very interesting point, because if you go to Galaxy Zoo, for example, one of the most famous things that was found there is called, what's the name of the person? Something like Hannes Object, or Hannes Zortfeig, because she was Dutch. So this was somebody who went to Galaxy Zoo, and they're asking you to classify things, and she saw an object that looked like if you see it, looks like a green man in space.
Yeah.
And so she then started talking about it, and it was actually through, and they had a chat site, and people realized this is an interesting class of astronomical objects, not little green men in space, but understanding what they were irradiated, and so there was a whole science. There were papers written about this class, and they had no idea when they put the galaxies up.
But can we stop the discussion? You were talking about different talk. It's called outlier detection, or rare object detection, right? What I present today is that given a bunch of candidates, people vote, and how we get these votes to get ground truth. If the people are not aware of a particular class, it will never show up. I agree, it will never. So if you want to create rare objects, either you do some outlier detection after we create the training set, and Raphael, we've done some work on that, and he's working on something similar. But I don't know. Maybe what you can do, you can create another. The other thing I could see extension to this is to create a question which is none of the above.
Yeah, no, just something.
And then you create a class of that. But that would be so contaminated that it would never be useful at that. I'm pretty sure, because none of the above would be a very, very wide spectrum of things. So I don't know how that would be useful in the training part of the model.
So you're saying different steps.
It's a different step. Once you have this one, then there's different ways of finding outlier in your data set. And that's my point. So,
Yeah, the purpose of classification is to describe the things you understand.
yeah.
To remove them, and then you look at things you don't understand,
Yes.
almost all which are always noise. Not all, but so many that you have to really want to look.
Yeah.
How well does your unsupervised learning recover the classes that you put in when you supervise? So can you find Cepheids versus RRI rate without telling them which is which? Just from clustering the data in some way.
You mean before I get the annotators?
Yeah.
Never try. I don't know.
'Cause
Just
they should cluster, right? They look good.
Just totally unsupervised.
Yeah.
I've done that a long time ago. If I remember, it depends on the clustering algorithm, right?
Yeah.
But
And the
not
features,
so well.
The whole point is that the size and features work for the clustering, right? That's what the annotators are for. Right?
No, the annotators gives me labels.
Well, they give you labels, and then the machine learning finds the features that match the
Yeah,
labels.
okay. So I think to answer this question, I would say, why will I ever do unsupervised learning if I have labels? It's so much better to have
Okay.
labels. Okay. So,
I'm just wondering what gain you get from all.
huge, huge. I mean, it's 30% easily, because they get mixed. Some of them may be separate nicely, but for example, Cepheid and RR, it depends which features. Cepheid and RLRs will be very close to each other. Some eclipsing binaries will be there. AGNs will be a little bit further up, but they will mix with some other, the young stars, they have similar stuff. So they do mix, right? It depends, of course, what features you use, but there's no doubt in my mind that they mixed, and you're not going to even come close to supervised. So that's why I want to have labels. Then I can do supervised. And to have labels, you need to get these people to do the work. Right? So that's the story. Supervised, I need labels. How do I get labels? I get a bunch of people to work. How do I get the best out of that? So that's kind of the rabbit path I follow here.
There may be other questions, but I know there was an announcement that we thought might be interesting to this group, so.
Yeah, so Maurus has given us a very nice introduction to classification in astronomical surveys, and on May the 4th we are organizing a mini workshop, one-day mini workshop on classification of X-ray sources, because as people might be aware here, there's the upcoming release of the version 2 of the Chandra Source Catalog and other missions that are coming online soon, which will give us lots of access to X-ray sources with a bunch of properties, and we want to try some of these techniques and start discussing possibilities for classification of X-ray sources. So if people are interested, there will be an email coming up later today. Let us know if you're interested in attending or maybe presenting methods for that. Thanks.
Thank you. So are there other questions for Pablo? Well, then I'd like to thank him for coming down and giving a very nice talk.
Thank you so much.